Welcome back to our 6.2 lesson on solving quadratics by graphing. Now, up to now we've just been solving our parabolas and finding exactly where they cross. And one thing to recognize or realize here is a solution to a quadratic function is going to be called a root. So we say we have one root, two roots, or no roots in these situations. Sometimes the roots are not going to be exact numbers on the graph though. If this happens, we just need to estimate the value of the roots. And to show this, we are going to use one quick example here. Again, we set up our table of values for our function x squared plus 2x minus 2 is 0. Negative 3 squared becomes 9, plus 2 times negative 3 is negative 6, and minus 2 leaves us with a 1. Negative 2 squared is 4, plus 2 times negative 2 is negative 4. Subtract a 2, becomes negative 2. Negative 1 squared is 1, plus 2 times negative 1 is negative 2. Subtract a 2 there, becomes negative 3. Oops. 0 squared plus 2 times 0 is 0, minus a 2. We're back to a negative 2 there. 1 squared is 1, plus 2 times 1 is 2, and minus a 2. These ones cross out, and we're left with just 1. 2 squared is 4, plus 2 times 2 is 4, minus 2. We have 6. 3 squared is 9, plus 2 times 3 is 6, minus 2. And we get 13. Now in this case, looks like this one's going to be off the chart, so we don't need to use that one. So we'd say where x is negative 3, 1, 2, 3, we have a y value of 1. Where x is negative 2, we have negative 2. Where x is negative 1, we have negative 1, 2, 3. Where x is 0, we have negative 2. Where x is 1, we have 1. And where x is 2, we have 1, 2, 3, 4, 5, 6. So it looks like this is our parabola. And like before, we can see that there are two places where it crosses, so a number of solutions is 2. In this case, though, it doesn't look like they're crossing at exact points. It looks like they are kind of in between some values there. Now, in later on lessons, we'll learn how to find exactly what these values are, but for now, we would just say that if we called this our first solution, our x sub 1, we would say that negative 3 is less than x sub 1 is less than negative 2, because it's somewhere in between negative 3 and negative 2. If this one was our x sub 2, our second x value that it could possibly be, 0 is less than x sub 2 is less than 1, because it's somewhere in between 0 and 1. So this is how we would write our solution set then, is these two here. And that's just, again, to show that we don't know exactly where it is. It's just somewhere in between those 2 points. If you wanted this one to be our x2 and this our x1, that's totally fine. You just have to make sure that they match up accordingly with where we have them on the graph and on our places there. So, how does this look in a real-world situation? Well, we have a real-world problem here. Mr. Anderson has no friends, but he likes going on vacations and taking pictures all by himself. He accidentally dropped his camera off the Eiffel Tower, which was 1,056 feet off the ground. How long did it take the camera to shatter on the floor, assuming there's no air resistance? Use the formula h of t equals negative 16 t squared plus h sub 0, where t is the time in seconds, and h sub 0 is the initial height above the ground in feet. So in this case, we'd say our h of t is what we're looking for. It's kind of like our our f of x function equals negative 16 t squared plus, well, we know our h sub o is 1,056 feet, because that's how far we started above the tower. So if we've got Eiffel Tower thing going on right here at the top, is where the camera was dropped, and it fell all the way down 1,056 feet. Now if you are a physics major, you'll notice that this negative 16 t squared, that's accounting for gravity. Negative 16 feet per second, that's how gravity is going to be pulling it down. And since it started from rest, there was no, nobody threw it down on the ground, there was no extra velocity, that's why there's no t term, there's only the t squared term, because that's our acceleration. And the end here, the 1056, that's its initial position. Anyway, if we wanted to actually graph this out, our graph is probably not going to be useful enough. I'm going to ask you to switch it up, and if you have a graphing calculator, I'm going to show you a good way to solve equations like this. So on this one is a TI-84 Plus. If you have a similar TI calculator, you can do something like this, where you get into your y equals format and you just punch in our, oops, too many, punch in what we have for an equation. So we had t, just use x in this case, so negative 16x squared plus 1056. So that's our formula for where we're starting at. Now if you kind of look over here at our little window, we can notice that already we see that it's not really going to fit too well on our graph. So I'm going to have you go over to the window and make sure that we're fitting everything in just right. We want our x minimum value to just be 1, so it only goes over so far. We want our x maximum value to remain 10, so that's going from negative 1 second all the way to 10 seconds. Our x min can stay at, or our y min can stay at negative 10, so we're looking a little bit below ground, but our y max, we're going to use 1,200 feet. So we're seeing as high up as 1,200 feet. And our x scale, we don't want it to go a tick every 1 mark, because there's a lot there. We'll do a tick every 200 marks. That way we'll be sure to fit everything in there. So from here, if we click on the graph and check it out, we can see over here that we have a nice workable graph. Looks like we started at 200, then 400, 600, 800, 1,000 or 1,000, and here is our 56, and it fell all the way down then, hit the ground over here, and that's at t equals 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds, 7, a little bit past 8 seconds. So if we wanted to draw that on ours, we would change these each to 100, so 100, 200, 300, 400, 500, 600, all the way up. 1,000, we'll even go 1 and make an 1,100. We started at 1056, came down, and according to that graph, it fell and hit just a little bit past 8. So what's happening here is the curve is getting steeper because gravity is pulling down on it as an acceleration, making it fall faster. So when it finally hit the ground, it was a little bit in between 8 and 9 seconds. So we could either say that 8 less than x, or should I say t in this case, less than 9, or we'd say that it hit the ground between 8 and 9 seconds. So it's good to know that my camera took about 8 seconds to fall to the ground.